Hi everyone, welcome back to another episode of liftandshiftdev. And today we're going to talk about Postgres database, and the topic is about the query plan from Postgres. And the query plan from Postgres is not the easiest plan to understand. That's why I'm going to show you the easy way to decipher the query plan from Postgres. To start with, I'm going to show you a really simple query plan. And this is the plan for select star from users table. It's basically loading up all the rows in the users table. In order to see the query plan, you just need to put the explain in front of the select query. And as you can see right here, the query plan is really hard to understand, but I have put a little bit of notes on the numbers, as you can see in the red text right here. So to start with, if you look at the course, it consists of two numbers. The first one is startup cost and the last one is total cost. And the cost is just a computational unit. It does not mean like CPU or something. It's just a computational unit used by Postgres. And as you can see, the startup cost 0. It basically means that in order to start up the node to run the sequential scan, is take around 0 computational units, and the cost to run the query in a total is 258 computational units. This is the expected total cost when you complete the query. And the rows, the output rows here is about 10,000 rows. So because we can do a select star from users, so basically it's going to return all the rows from users table, and you can see here is 10,000 rows for that table. And the width is basically the average of each row in bytes. So each row of the users table is around 122 bytes. And one thing to note is when you do explain, it does not actually run the query in the database. It's just a expected um, expected statistics to run the query. So all of these, it is an expected number, but it is not actually the number. The actual number can be different, but this just gives you an idea of how much computational units and how many rows and width of the row when you run the query. And sequential scan basically just like a um, linear search. So basically it's gonna go through each row table and compile it and then return back to the users. So I hope that easy to understand. And if you want to actually run the query and return the actual time and rows and anything else, you just need to put an analyze after the explain. So this actually gonna give you the expected um, statistics and also the actual statistics when it actually run this select query. So analyze actually run the query to the database. So I recommend when you do explain analyze, just run on development DB, not on the production DB, because if you run on production DB, it's actually run the query. So when I put analyze in this query, it's showing me the actual times. And if you, as you can see, the actual time is consists of also two numbers. The first one is startup time, and the last one is the total time. So the total time to run this query is 282 milliseconds. So this in millisecond. The number of rows that return is 10,000 that match the expected rows, and this only run once because you only scan through the table once. That's why the loops here only once. And so far we're talking about a really simple query plan, but how is actually the query plan is structured? So in Postgres query plan, it consists of 3 nodes. So 3 nodes, just imagine as the query plan is like a tree. If you look at this a more complex query plan, and the top 3 node gonna be the nested loop operation, and in this nested loop 3 node, it has a child node which is doing the bitmap heap scan, and then this bitmap heap scan node is got another child node called bitmap index scan. So basically, it's built up as a graph. And if you look at um, this query plan and look at the underline red line for all the node. So the easiest way to identify a node is the arrow in front of it. And if you look at all the text that with the red line underneath, and forget all the text here, it's gonna become like this, right? So if you go back here, look at the red line, and go back here. Basically, I just remove all redundant text, and this is all no left with it after the text removed. So if I imagine this node as a function, it consists of inner function. So the way the query plan work is it execute the most inner function first, and then it return the value to the outer function, and the outer function take that value and do some computation and so on. So basically here it's going to run a bitmap index scan first, and then bitmap heap scan takes the values returned from bitmap index scan, do some computational, return the value, and then it does the index scan, and index scan return a value, and then nested loop um, use these two values from bitmap in heap scan and index scan to do some kind of computational and then return back to the users. So I hope that makes sense. So I hope my analogy makes sense to you guys. Basically just an order of execution in the query plan. Alright, let's look at another query which is slightly more complex. So notice that I use buffers after the explain as well. It's going to show you how much memory buffer that used for this query. So the query here basically does is select everything from a tang1 table based on the condition unique 1 and unique 2. Unique 1 less than 100, unique 2 bigger than 9,000. And the way I work it out is I'll start with the top node and then find out the most inner node, which is these two bitmap index scan right here. And if you look closely, it's actually do index scan on unique 1 and unique 2 um, based on the condition unique 1 less 100 and unique 2 bigger than 9,000. So these two these two bitmap index scan are on the same level. So look at the first one, and the first one is the index scan for the condition unique 1 less than 100, and the expected cost is around 5 computational units. Expected row returns is 101, but the actual time when the query actually run is takes out 0.043 millisecond, and the actual rows return 100, which is different from the expected rows. This is normal because the expected is not the actual rows return, it's just expected from the explain, um, um, and then the number of times this index scan is just run once, and the buffer used is 2 blocks. So this is the share hits means that 2 block of cache hits, and 1 block is around 3 kilobytes. So this around total is around 6 kilobyte used for this bitmap index scan. So the second bitmap index scan is for the unique 2 based on the condition unique 2 bigger than 9,000. Again, similarly, the total time taken is 0.2 millisecond, and the actual rows return is around 1,000, and this run only once. And after these two bitmap index scans complete, it's going to return the results to the top node, which is the bitmap and node. And if you send so if you look at this, the share hit is 7, which just makes sense because it's a sum of 2 and 5 here, and so this is around 20 kilobyte in use for the total. And one thing I need to mention is that the top node actual runtime is a sum of all the actually runtime of the inner node. So if you look at here, this is 0.043 and this is 0.227. If you sum these two up, it's really close to 0.3. And after it's doing an AND operation for the 100 rows returned from the first index scan, and 1,000 rows from the bitmap from the second bitmap index scan is result to just 10 actually rows returned for the another bitmap heap scan outer node. So the AND operation for the results from these two bitmap index scan is just 10 rows, and the cost is 25 computational units, and the total time is just 0.3 millisecond. And all the results return back to the bitmap heap scan on the Tang1 table. And as you can see, the cost here is 25, expected cost is 25.08 as a startup cost, because the bitmap index and takes a total of 25.08 computational units. That's why the startup cost here start at 25, and the actual row return is 10, and this bitmap heap scan only run once. As you can see, the total time is 0.34 millisecond. And as you can see, this 0.34 second really close to 0.4 millisecond execution time. Because if you take this number and sum with the 0.08 millisecond, it's going to give you this 0.423 millisecond number. I hope that makes sense, and if you like this video, and please give me a like and subscribe to my channel. And I hope my explanation on this query plan work well for you guys. And if you don't understand, give me a comment, and I'm gonna give my best reply and to explain this further. Thank you so much, guys.